So in this section here, we talk about bifurcation in one-dimensional equations. In a single equation, okay, in a single equation. So bifurcation is always in terms of a parameter, sometimes two, but in this course we only talk about one parameter. The first type of bifurcation is what we call saddle node bifurcation. This one is simply refers to the case where the equilibrium are being created or destroyed. Okay, so this is the basic mechanism. This is a basic bifurcation by which equilibriums are created or destroyed. Notice here we are not focusing on the stability type. Whenever the parameter passes some threshold and there are some equilibrium pops up instead of none, then we call this saddle node bifurcation. And here's a quick example. Okay, here's a simple example. Single equation, right? So we call this x, one parameter. I will use this as an example. The parameter is r. So r is what we call bifurcation parameter. We want to find out what happened when you vary this parameter. R is the bifurcation parameter. So we obviously do this by the phase 9 analysis. We have the x-axis here. So we want to find out the number of equilibrium, which is really the graph of r plus x squared. So here's one case, one possible graph of r plus x squared. And it intersects the x-axis, this point, and then here. All right. So obviously this graph for the parabola looks like this. R has to be negative. Okay, R has to be negative. And the two equilibriums are positive or negative square root of negative r. Okay, so you can set this equal to 0. You solve for x, that's what it will be. But r has to be negative. Phase 9 analysis, so r prime here is positive. Okay, x prime on this side, x prime on this side is positive because the curve is above the x-axis. Right arrow. In between, x prime is negative because the curve is below the x-axis. And on this side is positive again. So when r is negative, okay, when r is negative, we have two equilibrium. One equilibrium is stable, the other equilibrium is unstable. Not that the stability type matters. It actually does not matter in this case here, but we just mention about this. When r is 0, okay, when r is 0, when r is 0, this is how the graph of r plus x squared look like when r is 0. It touches the x-axis right here, and this is the only equilibrium. Okay, this is the only equilibrium. At x equal to 0, okay, at x equal to 0. Moreover, we can call this semi-stable, because on one side it's coming in, on the other side it's moving away from this guy. So this is semi-stable. In some of the textbook, they for the semi-stable equilibrium, sometimes they use like a half-field circle, okay, half-field circle. Stable, we use a field circle. Unstable is a empty circle. So when R is negative, 2 equilibrium, R equal to 0, 1 equilibrium, and when R crosses 0, okay, when R crosses 0, you have the third case. That is, there is no intersection and there is no equilibrium. Okay? So the fact that when R crosses 0, okay, when R crosses 0, the amount of equilibrium changes from 2 to none, okay, changes from 2 to none. That's what we call a saddle node bifurcation, okay? So we say a bifurcation occurs at R equal to 0. So bifurcation is a huge change in the behavior of the system. It has gone from 2 equilibriums to 1, okay, to 1. So now I will talk about the bifurcation diagram, okay, bifurcation diagram that we briefly mentioned before, and some people have a hard time understand it. So here let's talk about this bifurcation diagram. Bifurcation diagram, it is the stability of equilibrium in terms of the bifurcation parameter. So the horizontal axis is always the parameter. So here we call this R. The vertical axis is for the variable here, because it's for x. We're going to plot the graph of equilibrium as a function of what? As a function of R. Okay, as a function of R. So when R is greater than 0, there is no equilibrium. There's no equilibrium. When R is less than 0, so here on this side is R less than 0. The equilibrium is given by positive square root of negative R and negative square root of negative R. So both of them are square root functions. And they look like this. So this is the upper branch of equilibrium. It's positive square root of negative R. And below, you have negative square root of negative R. So there are two equilibriums for negative R. When R is 0, there is one equilibrium. When R is positive, there is no equilibrium. So there is no curve on the right side here. Furthermore, on this so-called bifurcation diagram, I like to indicate which equilibrium is stable, which one is unstable. The positive one, okay, the positive one is unstable. For unstable equilibrium curve, okay, for unstable equilibrium curve, we use dotted line. If it is stable, we use field line, okay, so we use a solid line, okay, we use a solid line. So the upper branch, so these are equilibrium that's not stable, that's unstable. And this is the branch that is what? That is stable, okay, that is stable. And this is what we call a bifurcation diagram. Bifurcation diagram. And we claim that a bifurcation occurs when R crosses 0, because on the left side, it's basically the same, even though the size of the equilibrium changes, but there are always two equilibriums. One is unstable, the other one is stable. But when R crosses this threshold at 0, there is no equilibrium. Okay, there is no equilibrium. So this is what we call bifurcation diagram, and this is the bifurcation diagram for saddle node bifurcation. Okay, saddle node bifurcation. All right. A simple example show that this problem. So notice it looks different from the prototype problem. Okay, notice it's different from the prototype problem, but there is still just one parameter R. show that this guy undergoes saddle node bifurcation. As R varies. And also find out the bifurcation point, or find out the value of R at the bifurcation point. So saddle node bifurcation, once again, means we need to study the amount of equilibrium. So how do we study the amount of equilibrium to this guy? So obviously we have to solve this equation. We have to set this equal to 0. That'll produce the equilibrium. Obviously you have different choices. You can view this as just the graph of this simple curve, which is actually not that simple. You want to look at where this guy equal to 0. Or this is also equivalent to say R equal to x plus e to the negative x. So I'm going to be looking at the graph of this horizontal line and the graph of this guy. Try to figure out where they intersect. The third option will be, this is identical to this equation. I simply move this guy to the right side. So that'll be a straight line, and that'll be the graph of e to the negative x, which is something we're kind of familiar with. So that'll be the approach we're going to take. Okay, we're going to look at the graph of this guy and this straight line and see where they intersect. So let's take a look at some preliminary analysis here. We take a look at the graph of e to the negative x. E to the negative x. So you take out your calculator and you can easily plot it. Okay, it's e to the negative x looks like this. When x goes to positive infinity, this guy drops onto 0. When x goes to negative infinity, this guy goes to infinity. R minus x, the slope is a constant, but it intersects the y-axis at R, right? Intersects the y-axis at R. And the slope is always what? Is always 1, okay? So that's one potential case. And notice for this example here, we have how many intersections? 2, okay? There are 2 intersections, meaning there are 2 equilibriums. So when you vary this R, all right, when you increase the R, there are still 2 equilibriums. When you decrease your R, well, did you notice what happened at this critical moment? That is when this curve, this straight line, is tangent to this critical curve, to this curve. There is this 1 equilibrium. So I will plot that right here. That's e to the negative x. So here's that critical moment where there is just 1 equilibrium. That is when this guy somehow is tangent to this, okay? Tangent to this. Tangent to this. I do not know what the tangent point is yet, but that's when we're going to have this bifurcation. R minus x e to the negative x. When you further decrease R, okay? When you further decrease R, this guy basically stays the same. When you further decrease R, you're going to be look at a scenario like this, okay? This is R minus x. And in this case here, there is no equilibrium. No equilibrium. So you can say, hey, based on the graph here, when R is bigger, when R is big, there are always 2 equilibrium. But when R is small, there is no equilibrium. So obviously, we're trying to figure out this critical scenario here, and that's the value of R at the bifurcation point. So how do I figure this out? How do we figure this out? So first of all, I want to figure out where there are tangent. So the slope of this guy is obviously, the slope of the straight line is obviously -1. I want to find out where the tangent line is where the tangent line has a slope of -1. So I differentiate this guy, I get negative e to the negative x. And I solve for x. So that means when x is 0, that's where the tangent line is what? Has a slope -1. Okay, that's when the tangent line has a slope -1. In other words, they're going to intersect. They're going to intersect at x equal to 0. They're going to intersect at x equal to 0. So to find the r value, we'll simply set x equal to 0. Think about this, okay? Think about this. When x is equal to 0, that's where they intersect. So they're going to equal there. That'll give you the r value, okay? That'll give you the r value. So r turns out to be 1. When r is 1, there is this unique equilibrium. So we say the bifurcation point is at r equal to 1. Okay, r equal to 1. When r is smaller than 1, no equilibrium. When r is bigger than 1, 2 equilibrium. Okay, so this is the bifurcation point. This is the bifurcation point. So that was one example of saddle node bifurcation. That was one of the saddle node bifurcation. All right. So our second type of bifurcation is what we call transcritical bifurcation. Transcritical bifurcation refers to the case where when you change your bifurcation parameter, the equilibrium will not be destroyed. The equilibrium will not be destroyed, okay? However, they may interchange the stability. They may exchange the stability. So when that happens, we call this bifurcation. We call this transcritical bifurcation. And I'll present the prototype equation without giving you any additional example. Okay, so we're going to look at this problem here. So once again, the equilibrium is the intersection of this parabola and the x-axis. So here I do a quick phase line analysis. The graph of rx minus x squared obviously depends on r. Okay, when r is negative, the parabola is opening downward, and it's kind of on the left side of this y-axis. So here is one of the equilibrium, that's r, okay, and this is 0. When r is negative, this equilibrium is on the left side, okay, on the left side. Phase line analysis, this part, okay, this curve is below the x-axis, so x prime will be negative over here, okay, on this side. Use an arrow pointing away. In between is an arrow pointing to the right. Similarly, this one is pointing to the left. So that reveals this equilibrium is stable, and this equilibrium is unstable. This one is stable. So for stable equilibrium, I use a field dots, otherwise a circle. When you increase the r to say r equal to 0, so you're talking about the graph of, well, negative x squared. And that's how the graph looks like. So now there is just one equilibrium at 0. So that's kind of the critical value here. That's the bifurcation point. And this equilibrium, it is, well, semi-stable, okay? Semi-stable. We're going to call this semi-stable. Use like a half-field dot. Because to the left side, it'll move away. to the right side, it'll move into this equilibrium. And now when R crosses this threshold, okay, when R crosses this threshold to the positive region, there are two equilibriums. One is still at 0, but the other one is positive. All right. So similarly, this one, 0 becomes unstable. This one is negative, point to the left. This is positive, point to the right. So this guy is unstable. R here is stable. R here is stable. So if you pay attention to what happens to the 0 here, 0 has changed from a stable equilibrium to unstable. Or, all right, even though this guy is negative, this guy is positive, but this is still R, okay? This guy has changed from unstable to stable. So the bifurcation diagram for this transcritical bifurcation look like this, okay? Here's the bifurcation diagram. Once again, we have the horizontal axis being the bifurcation parameter R. Vertical axis is the variable X. So there are two equilibriums, okay? Two equilibriums. One is always 0 here, okay? One is always 0. In other words, the horizontal line, okay? This is where X equal to 0. The other one is X equal to R, okay? The other one is X equal to R. So which is always a straight line? This is X equal to R. This is also X equal to R. So two equilibrium, okay? So this is one equilibrium. That's another one. This one does not depend on R. It's always 0. It's always X equal to 0. And this one depends on R. And it's always given by this equation, okay? X equal to R, okay? X equal to R. And now let's write down the stability. We're going to denote the stability on this bifurcation diagram. When R is negative, so on this side, okay? This side is for R that's negative. 0, okay? 0. 0 is stable, okay? 0 is stable. So we're going to use a solid line, okay? 0. This branch of equilibrium is stable. X equal to R, it is unstable. So we use dotted line. Dotted line. When R crosses this threshold to become positive, X equal to 0 becomes, well, unstable. See, this one is dotted, that I left it dotted line. This one is unstable. X equal to R, however, becomes what? Stable, okay? This one is stable. 0, unstable. On this side, however, it was stable. This lower part, it was unstable. All right? So that's why we call this a transcritical bifurcation, because the stability has interchanged. 0 has gone from stable to what? Unstable. X equal to R has gone from unstable to stable. All right, so this is the transcritical bifurcation diagram. So once again, whenever the equilibrium interchange stability, we call this transcritical bifurcation. All right, the third type of bifurcation we're going to talk about in one dimension is what we call pitchfork. Pitchfork bifurcation. Well, if you think about the shape of a pitchfork, you have a handle and you have, well, the forks part. Pitchfork bifurcation refers to the case where the amount of equilibrium changes from 1 to, say, 3, okay, to, say, 3. And there are two types of pitchfork bifurcation. The first type is what we'll call supercritical. And later I'll explain why we'll call this supercritical pitchfork. Once again, I will give you a prototype problem, okay? And this problem looks like this. So the right side is this cubic polynomial. Once again, we try to plot the graph of Rx minus x cubed. Here how it looks. So you can take out a calculator or plug in some R and figure out the graph of this. When R is negative, this is how actually Rx minus x cubed look like. All right. If you are not sure about this, okay, try to plot it and see why the graph look like this. So there is only one equilibrium, and this guy is being stable. Okay, being stable. When R equal to 0, actually not much happening. Because R equal to 0, the graph still looks like this. Basically, it's negative x cubed. There is still just one equilibrium that is being stable. Now let's see what happens when R crosses 0 to positive. So this equation, okay, if you want to factor this, you will be able to see this better because you can factor out an x, and back there you have R minus x squared. You see? So x equal to 0 is always an equilibrium, but when R is negative, there won't be any other equilibrium. But when R is positive, this part can be said to be 0. The graph of Rx minus x cubed looks like this. There are 3 equilibriums now. This one, you can solve it, okay? This one turns out to be negative square root of R. That is still 0. And that's positive square root of R. You can further use the phase line to figure out this guy is being stable. This one becomes unstable. And this one becomes what? Stable. All right, this is stable. So we look at the amount of equilibrium in this example here. It has gone from 1 equilibrium to 3. Moreover, those equilibriums become stable. And that's what we call this supercritical. Okay, supercritical. Here's the bifurcation diagram. Horizontal axis is the bifurcation parameter R. 0 on the left side, so when R is negative, it's always just x equal to 0. So this guy is always stable. Here's your x-axis. On the right side, you have 2 branches. You have the upper branch given by square root of R. That is being stable. Stable, solid line. On the lower branch, lower part, negative square root of R. That is also what? Stable. And x equal to 0, it's still there, still equilibrium. It just becomes what? Unstable. So this is x equal to 0, guys. All right. Stable. This is x equal to 0 being stable. Upper branch, stable, stable. And this one becomes what? Unstable. Unstable. So this one we'll call this supercritical. When the 2 equilibriums that you created become stable, okay, it's stable. Now, supercritical pitchfork. The second category is subcritical, when those 2 branches becomes unstable, okay? And here's a prototype problem. Subcritical pitchfork. prototype problem. Prototype problem. I mean, not all the equilibriums are at 0, for example. Okay, they may be somewhere else, but as long as this is how the bifurcation diagram look like, we will call this supercritical. Okay, subcritical, Rx plus x cubed. So you can do similar analysis. Turns out for this problem here, when R, okay, when R, so once again horizontal axis, the R axis, when R is positive, there is only one equilibrium. When R is positive, there is only one equilibrium that is unstable. Okay, so this is really just x equal to 0. Okay, that is unstable. So you guys can carry out this analysis by yourself. Okay, figure out the formula for equilibriums and see how it looks and why it's stable or unstable. The upper branch, this is square root of -4, I guess. The lower branch is negative square root of -4. They are both being unstable. Yeah. But 0 becomes stable. Okay, 0 becomes stable. The guy in the middle is stable. Yeah. So the fact that those two guys are unstable, that's why we call this what? Subcritical pitchfork. Subcritical pitchfork bifurcation. So these are typical bifurcation problems in one dimension. Our next topic will be what happened in 2 dimension, and that'll be our final topic. That'll be our final topic.